Hello students, welcome back to the channel. So in this video you're going to be handling or starting ionic together with metallic bonding. Now this is going to be taught under bonding and structure, and you're going to be covering mainly ionic together with metallic compounds. So this video is going to be mainly for ionic compounds, and the next video is going to be covering metallic compounds together with polarization power. Starting this video, just a preview in the previous video, we are looking at radioactivity. So we looked at radioactivity together with its applications. And this video is suitable for students only in Form 5, the new curriculum. So you're going to look at bonding and structure, or formation of ionic bonds together with ionic compounds, together with their features and characteristics. And the topic is going to be divided into two videos. So you're going to have video 1 and then video 2. So the topic has been presented to you by Olgembe Yusuf, and you advise subscribe to the channel, share the video to your colleagues, and ensure that you like the video. Now starting, we are going to say that the competence that you're going to be looking for under this topic is going to be, as a learner, you should be able to analyze the different types of chemical bonds together with their molecular structures. And then from there, you have to relate them to the given properties together with the uses of the substances that can be applied in real life contexts. Now let's start with the formation of ionic bonds together with metallic bonds. But I say that for this starting video, we are going to be mainly looking at ionic compound formation together with the characteristics and also the scenarios or items that can be examined under this subtopic. So by definition, anion bond is going to be the same as an electrovalent bond, and it's going to be formed simply by complete transfer of one or more electrons from one atom to another, which in turn creates oppositely charged ions. So with this, we are meaning that for it to form an ionic compound, just like you're hearing ionic is containing a word of ion. That means that you have to have a positive ion together with a negative ion for such a compound to be formed. So the complete sharing of electrons, whereby a cation gives off electrons to an anion, or a metal atom gives off electrons to a non-metal atom, is what we call complete transfer of one or more electrons, forming oppositely charged ions. The one that donates protons, which is always the metal element, becomes the cation, and then the one which accepts protons or electrons becomes an anion, and that's how we form an ionic bond. That means that it's going to be a bond which is between a positively charged element together with a negatively charged element. And you'll say that an ionic bond is also the same as electrovalent bond. So it's going to be formed simply by complete transfer of electrons from one atom to another, creating oppositely charged ions. Like I said, it's the metal which donates electrons and becomes a cation, and then that one that accepts electrons becomes an anion. Now proceeding, let's look at electron transfer. Now we are going to say that here the metallic element is one which is going to lose electrons and therefore becomes electropositive ion, which I've just explained, which is called the cation. And then the non-metallic element is the one which gains electrons and then it becomes an anion. So an anion is that ion that has recently accepted electrons, whereas a cation is that ion that has recently lost electrons. So looking at the now the bond that is formed, the ionic bond, is going to be held by since it's between a positive charge and the negative charge, is going to be held by what we call the electrostatic force of attraction. And with this, we are going to say that both the cation and anion are going to be held together by strong electrostatic forces of attraction, simply because the bond is formed between a positive ion and a negative ion. Now proceeding, we are going to say that an ionic bond is also going to be called the electrovalent bond, which I have mentioned earlier, and it's going to be formed by a complete transfer of one or more electrons from one atom to another, forming oppositely charged ions. We have already cover this. So let's look at one example under which an ionic bond or an ionic compound is formed. So for an ionic compound to be formed, you need to have a metal together with a non-metal. So chloride is a derivative of chlorine, which is a non-metal. Sodium is a derivative of sodium element, which is a metal. So these two, sodium and chlorine, share electrons between themselves to form an ionic bond, which gives an ionic compound of sodium chloride. So in the outermost shell of the sodium atom, we have what we call one electron. So what happens, we have said that first to form an ionic bond, a metal element has to donate electron to a non-metal element for a bond to be formed. So that's why on the outermost shell of the chlorine atom, we have 7 electrons. So for this shell to be stable, it requires 1 electron. That's why sodium donates 1 electron to the chlorine outermost energy level. And when this happens, we form what we call a bond between the two, whereby sodium, after losing this electron, it remains with the outermost energy level to be completely full of electrons and is being stable. That's why we put here plus sign to show that it has lost an electron. And here we put a negative sign on the chlorine atom to show that it has gained an electron. And this is the structural representation. So the bond that is being formed between these brackets is what we call the ionic bond. And all of them together combined is what we call the ionic compound. So you're going to say that the sodium atom has an electronic configuration of this, together with the 3. If you look at the electronic configuration of sodium, the 3s subenergy level is only having 1 electron, which makes it very unstable. So this electron is easily going to be lost to the chlorine atom, forming an ionic bond. That's why we proceeded and say that this electron is transferred to the chlorine atom by sodium to form, first of all, to gain stability, because if you look here, after sodium losing that outermost electron, it obtained a stable octet or subenergy level, and that's what we call gaining stability or gaining a noble gas configuration means. And then you write the configuration, you also write the process that led to the formation of the sodium ion, whereby you write the sodium atom donating 1 electron to gain a stable electronic configuration, but gaining a plus sign on the sodium atom to show that an electron has been lost. So with chlorine, it's going to be quite the opposite. Instead of donating, for it accepts, because for non-metals in ionic bond formation, for them they just accept protons. So what you have to do first is we have to describe the chlorine atom, and you also state its electronic configuration. But if you look at 3p subenergy level, you realize that for it to be full, we need to borrow an electron. So that's why I say that the 3p subenergy level has only 5 electrons, and therefore it's unstable. So for it to regain its stability or a noble gas electronic configuration, it has to gain this electron, which has been released by sodium, so that it can go on to this 3p subenergy level. And when that happens, we gain a noble gas electronic configuration, which represents this structure up here. And with that, that means that the chlorine atom is now stable. But since it has gained an electron, it becomes the chloride ion. And we simply say that this electronic configuration is going to represent the chloride ion. And we do an equation to represent what you have written in the structure above, showing that chlorine atom is gaining an electron to form the chloride ion. Now proceeding, let's look at the electron arrangement. So here you're going to say that the electron or electrons are going to be transferred from a metallic element, just like we said. You have seen sodium together with chlorine. Sodium is a metal element. Then chlorine is a non-metal element. So when you're forming an ionic bond, electrons come from the metallic element to the non-metallic element. And this is done purposely to gain a stable electronic configuration on each of the atoms. And when that happens, we form what we call an ionic bond. But also the one that has lost electron becomes positively charged, and the one that has gained electrons becomes negatively charged. And therefore, That's why we say that since this one is going to be positively charged and this one is going to be negatively charged, the bond that is going to be formed between them is called an ionic bond because it's between ions, but also it's going to be held by electrostatic forces of attraction simply because it's between ions of opposite charges. I hope that's understandable. So proceeding, I'm going to say that the electrons are going to be transferred from a metallic element to a non-metallic element. The element that is going to lose electrons is going to become electropositive, or it's going to become positively charged, since it forms a positive ion. And also the element that gains electrons is going to be electronegative, or it's going to be negatively charged, since it forms a negative ion. So the cation and anion are going to be held together by strong electrostatic forces of attraction. And you have said that the reason for that is because the bond that is being formed is joining ends of different charges, one positive and the other negative. So the forces holding ends of different charges are called electrostatic forces of attraction. So proceeding, let's look at the giant ionic structures. So in giant ionic structures, the metallic elements are going to combine also with the non-metallic elements. However, the ionic bonds that are going to be formed in these compounds are going to have extremely strong electrostatic forces of attraction, simply because of the opposite charges that are present on the ends. And you have already explained that, but you're going to look at the magnitude. For example, if you're having magnesium chloride, if you look at magnesium forms a charge of 2 plus. And if you look at sodium forms a charge of plus 1. So since the magnitude of the charge on magnesium is greater than that on sodium, we are going to say that magnesium chloride is having a giant ionic structure as compared to sodium chloride, simply because in magnesium chloride, the magnitude of the charge is greater or steeper. So we're going to proceed and say that each ion is surrounded by the greatest number of oppositely charged ions called the coordination number. So looking at the examples of the giant ionic solids are going to include sodium chloride, calcium chloride together with zinc sulfate. And you're going to look at that in details further in the video. Now proceeding, let's look at the properties of these ionic compounds. Now one of the property of ionic compounds that is well common, or that is only a distinguishing factor between other compounds and ionic compounds, is having high melting together with high boiling points. So if you look at all ionic compounds, they are going to have high melting and high boiling points, and the reason for that is because the electrostatic forces of attraction joining their ends are very strong. So therefore, high amounts of energy are going to be required to break the bonds holding such ends. So ionic bonds have high melting and high boiling points simply because electrostatic forces of attraction joining the ions are very strong. So for you to break them, to reach the melting point or the boiling point, you require a lot of energy, which in turn results into high melting and high boiling points. So proceeding, we can also look at the good electrical conductivity that is present in their molten and aqueous states. Now, one thing you should note here is that ionic compounds, they do not conduct electricity in solid format, simply because ions are locked up. Consider crystals of salt. For example, you have seen copper to sulfate. These salts, in terms of solids, they are crystalline in nature. So if at all they are crystalline in nature, we assume that the conducting particles of electricity are going to be locked up within these solids. So for you to relieve them, you need to dissolve these solids in water to make it aqueous, or you need to melt these crystals so that it can get in liquid state. That's the only way electricity can be conducted. But if at all they are not in molten or aqueous states, they cannot conduct electricity. That's why when you're giving this feature, when you're giving this characteristic, you need to include this state, that they are good conductors of electricity only in molten and aqueous states. And the reason for that is because in molten and aqueous states, ions are going to be free to move and conduct electricity. Also, they are going to be very soluble in polar solvents. Polar solvents, mainly we use water for this level. So I'm going to say that the ion solvent interactions are stronger than the ion-to-ion interactions in the solid state, which is going to enable their solubility. However, we are going to dive deeper into each of them in details. Now, they exist as crystalline solids at room temperature. Majority of the ionic compounds, they are going to exist as crystalline solids at room temperature. And this is because the strong electrostatic forces of attraction cannot be overcome by the room temperature. So they keep themselves in solid state due to the strong electrostatic forces of attraction closely holding their ions that enable them to exist in solid state. Now, this is a more detailed table format of which you can summarize this. So one, high melting and high boiling point, and it's going to be because of that. Like I said, it's a summarized table of what you have just discussed. So you just pause the video and then you draw that table. So after doing the table, like I said, all these properties, the four of them, you have already discussed them. So after pausing the video and then summarizing your table, let's proceed to the next property. Now let's look at electron transfer. Now we have said that for ionic bonds to be formed, a metal loses electrons and a non-metal gains electrons. The one that has lost electrons becomes electropositive, or it becomes positively charged. And the one that gains electron becomes negatively charged, or electronegative. So what does electron transfer mean in terms of ionic bond formation? So looking at this, we are going to say that ionic bonds ionic bonds are going to be formed when a metal loses electrons to a non-metal, resulting into formation of positively charged cations and negatively charged anions. So in a defining electron transfer, you are going to relate it to ionic bond formation. For instance, you are going to say that ionic bond formation is going to refer to the instance or the process by which metals lose electrons to non-metals, forming electropositive cations and also forming electronegative anions. That's what electron transfer is going to mean. And you only transfer electrons in ionic compounds. Now looking at electrostatic forces, remember that electrostatic forces, these are going to be forces that are holding ions of different charges, positive and negative. So you're going to say that the cations together with the anions are held together by strong electrostatic forces of attraction. The reason why we use cations and anions is because cations are positively charged. So you can, instead of writing cations, you can say the positively charged ions and the negatively charged ions, because cations are positively charged ions coming from metals, anions are negatively charged ions coming from non-metals. So with that, let's look at a sample question under that. So one Sarah is conducting an experiment in the chemistry lab and she observes that when sodium metal reacts with fluorine gas, a white crystalline solid, which is sodium fluoride, is going to be formed. So one, we are going to be using electronic configuration to explain how this ionic compound or how this ionic bond is going to be formed between the sodium atom and also the fluorine element. Then in Roman number 2, you're going to justify the role of the electrostatic forces of attraction holding the sodium and the fluoride ions together, forming the sodium fluoride compound. Then later we are going to predict what is going to happen if sodium fluoride is dissolved in water and explain why. Remember that we summarized this in the table. Now let's look at the response. Formation of ionic bonds between the sodium and the fluorine atoms. So here we are going to be quite sensitive because we are describing ionic bond formation and we have already looked at the process. Now here I didn't draw the other structure because the structure is unnecessary. All we need is a full elaborative essay presenting your explanation, and you saw that ionic bond is going to involve loss of electrons to gain a noble gas electronic configuration from the metal to the non-metal. So we're going to respond to that in accordance to our notes, and we're going to say that sodium first, it has an atomic number of 11. Now this is going to give it an electronic configuration of this. Now the reason why I gave the atomic number is to highlight you onto what, or is to highlight the person marking you or the examiner about the electronic configuration you're going to be rating, because you use atomic number to rate the electronic configurations. So after stating its atomic number, you have to set its electronic configuration. Now this is going to mean that if you look here, the outermost energy level of sodium is the 3s subenergy level, and it has one electron, which is very unstable. So it has to lose that electron to gain a noble gas electronic configuration. So you're going to talk about that. So you're going to say that this means that sodium has one electron in its outermost shell or energy level or subenergy level. And then if you look at fluorine, fluorine has atomic number 9 and the electronic configuration this. If for the p subenergy level to be stable, it has to be either full with 6 electrons or it has to be half filled with 3 electrons, but it only has 5. That means that it's lacking 1. So for it to gain a stable electronic configuration or a noble gas electronic configuration or a stable octet or a stable subenergy level, it has to gain 1 electron to complete its stability, achieving a stable octet. So you're going to join these statements together to show how an ionic bond can be fully formed. And you're going to say that, therefore, when sodium reacts with fluorine, sodium is going to lose its single valence electron from the 3s subenergy level or orbital, which results in the formation of a sodium ion. Because after losing an electron, we have to form an ion. And the charge which you write up here is going to depend on the number of electrons you have lost. So since we lose one ion, 1 electron, we have to form positive 1. If we lose 2 electrons, we have to form positive 2, because at some other point, we may ask you how magnesium chloride is formed. So with a positive charge. And on the other hand, fluorine is going to gain that electron that sodium has lost to form the fluoride ion with a negative charge. So the electron transfer from sodium to fluorine is going to create positively charged ions, and that's going to be the sodium ion together with the fluoride ion. Now from here, what I missed out that may add you marks is writing the equations of how these two ions are formed. You write the equation for sodium, showing that sodium has formed the sodium ion plus losing an electron. And then you also write the equation for fluorine gaining the electron which sodium has lost to form the fluoride ion. That's going to add you a maximum of 2 or 3 marks. So I make a conclusion that these ions are going to be held together by electrostatic forces of attraction, simply because the bond that's going to be formed is between oppositely charged ions. Like we said that electrostatic forces of attraction are going to be those forces of attraction that exist between ions of different charges, positive and negative. So it's going to be between positively charged sodium ion and also the negatively charged fluoride ion, forming an ionic bond. Now this results in the formation of sodium fluoride. This is an elaborative essay of how you can present your answer. Now let's look at the role of electrostatic forces in holding the sodium fluoride together. So here we are going to say that in sodium fluoride, the sodium ion together with the fluoride ions are going to be held together by the strong electrostatic forces of attraction, simply because they're between oppositely charged ions. And the bond that is going to be formed between them is going to be called the ionic bond. So these forces, they can occur because they are holding opposite charges of ions that attract each other. They are strong because if you look at the laws of attraction, laws of charges, they tell you that unlike charges attract, whereas like charges repel. So these electrostatic forces of attraction, they are going to be very strong simply because they are holding ions of opposite charges, and opposite charges attract each other. So their strength together with the attraction strengthens the bonds of ionic compounds. So we're going to proceed and say that the sodium ion has a positive charge due to the loss of an electron, whereas the fluoride ion has a negative charge due to the gain of an electron. And the electrostatic force of attraction between these opposite charged ions is going to create a stable ionic compound, simply because the ions are attracting each other, and also the electrostatic forces of attraction, they are being favored in the attraction direction. So proceeding, we are going to say that the stronger the charge on the ions, the smaller their ionic radii, and the stronger the electrostatic force, together making the ionic bond in sodium fluoride particularly strong. We are going to look at this more in details in the next video. Now looking at part C, what is going to happen when the sodium fluoride dissolves in water. We have already summarized this in the table. So we're going to simply say that when sodium fluoride is dissolved in water, it's going to dissociate into its constituent ions. Simply, any ionic compound, since any salt which is formed between a metal and a non-metal is going to be an electrolyte. And what electrolytes do, just like you're taught in electrolysis, they split to give off the respective ions that are going to be present in such a compound. So you're going to have the sodium ion together with the fluoride ion. So these ones are going to be coming from sodium fluoride. So we're going to say that dissociates into its constituent, which is sodium ion, together with the fluoride ions. So this is going to happen because the water molecules surrounding the sodium ions and the fluoride ions effectively break down the ionic bond between them. Now here remember that we say that for anything to dissolve in water, it must be polar. That means that it must form bonds with the water molecules. So the process is going to be explained in terms of polarity of the water molecules. And you're going to say that water being a polar solvent, meaning for something to be polar, let me elaborate using a bond. For example, if I have a bond between the chlorine atom and another atom, for us to call this bond that is polar, one of them has to have a partial negative charge and the other one has to have a partial positive charge. We shall look at this under organic chemistry. So we're going to say that water is a polar solvent, meaning it has a partial positive charge on the hydrogen ions or the hydrogen atoms and a partial negative on the oxygen atoms. So the positive sodium ions are going to be attracted to the negative part, which is going to be the oxygen. If you are to draw the water molecule, it's going to be in this format. So the oxygen is more electronegative than hydrogen, so it's going to have the partial negative, and then hydrogen is going to have the partial positive. So when these ions dissolve in water, when the sodium fluoride dissolves in water to give off the sodium ions and the fluoride ions, the positive ions get attracted to the partial negative, and then the negative ions get attracted to the partial positive. That's what we are describing here, that the sodium ions are attracted to the negative side, which is the oxygen of the water molecules, while the negative fluoride ions are going to be attracted to the positive side, which is the hydrogen ions of the water molecules. So this interaction between the water and then the ions of sodium fluoride is going to enable dispersion of the sodium together with the fluoride ions in the solution, making dissolution of sodium fluoride possible in water. And that's how salt dissolves in water. So for anything that dissolves in water, it must be polar. It must have the positive ions together with the negative ions, which can interact with the oxygen atoms and hydrogen atoms present in the water molecule, just like we have seen on this part. So we're going to conclude that that's when sodium fluoride is dissolved in water, it's going to form a solution of sodium ions together with the fluoride ions in water, simply because all ionic compounds are polar in nature. They can give off ions in terms of negatives and positives that gets attracted to the negative part of the water, which is oxygen, and the positive part of the water, which is the hydrogen atom. Now let's look at question 2. Now in question 2, we are going to say that Alex is preparing a solution by dissolving table salt, which is sodium chloride, and also sugar, which is the same as glucose in this format, and is going to notice the following. 1, it notices that sodium chloride conducts electricity, but glucose or sugar does not. So question 1 or task 1, you are going to explain why sodium chloride is able to conduct electricity in solution, but sugar can't. And then part B, we are going to compare the structural composition of sodium chloride together with sugar. And then in part C, we are going to, based on bond strength, to explain why sodium chloride has a higher melting point than sugar. Remember, I told you that any compounds have the highest melting and boiling points, and we have already gave the reason for that. So let's look at how we can approach a question if it has been presented in that format. So proceeding, let's look at the response that can be objected to such a scenario. So when you're going to explain why sodium chloride is conducting electricity in solution, but sugar is not conducting electricity. Remember, for electricity to be conducted, there must be positive ions and negative ions. So you're going to base our explanation on that. And you're going to say that in sodium chloride being an ionic compound, when it dissolves in water, is going to dissociate into its constituents. So it's going to give the sodium ions, which are going to be the positive ions in this case. And also it's going to give the chloride ions, which are going to be the negative ions in this case. So these ions that are given off from sodium chloride are free-moving ions. And since they are free-moving in solution, they are capable of carrying or conducting electrical charge, or what you can call electricity in solution form, which is going to allow sodium chloride to conduct electricity as a whole. But if you look at the water molecules being polar, they are going to surround the separate sodium ions and the chloride ions, facilitating their movements. It's because in the solution we are dissolving sodium chloride in water. Majority of the solution is going to be water molecules. And if you remember about what I've just explained about polarity, sodium ions interacting with the negative ions on water molecule on the negative atom, which is oxygen, and also the chloride ions interacting with the hydrogen ion or the hydrogen atom on the water molecule, facilitates their movement in solution. And when that happens, that means that they can easily conduct electricity in terms of solution or a pairs format. However, if sodium chloride is in molten state, or if sodium chloride is in crystalline state or solid state, electricity can't be conducted, simply because these conducting ions, sodium and chloride ions, they are going to be locked up in solid particles. That's very important. So on the other hand, if you look at sugar or glucose, it's a covalent compound. So when it dissolves in water, remember that all covalent compounds are nonpolar, so they cannot dissolve in water. Or when we put it in water, we cannot get positive and negative ions. So I'm going to say that it does not dissolve in water to give us the constituent ions. So instead, it's going to dissolve as a whole molecule. And if at all we don't get positive and negative ions, that means that such a compound like glucose cannot provide the conducting particles that are necessary for electrical conduction, and therefore electricity can be conducted in such a glucose or sugar solution. So we're simply going to make a conclusion that since there are no free ions, or since there are no free moving or mobile ions to move and carry electrical charge, the sugar solution is not going to conduct electricity. So let's look at part B, where we are going to compare between the structural composition of sodium chloride together with sugar. So starting, now different compounds have different structures. So ionic compounds mainly, they have what you call giant ionic structures, or what you can call ionic structures. Whereas covalent compounds, they have what you call covalent structures. So looking at the structural composition between sodium chloride together with glucose, we are going to give a brief explanation or a brief background about their structure data that they exhibit according to the covalent nature and then the ionic nature in either of them. So starting with sodium chloride, which can also be written as this, we are going to say that sodium chloride has an ionic structure. Now, after talking about the structure, you need to talk about what is a constituent, what are the components of that structure. So if we talk about ionic structure, what is it going to have? We expect an ionic structure to have ionic bonds, and we expect ionic bonds to have electrostatic forces of attraction, and we expect such a structure to have a high melting and boiling point. That's all you need to mention. Then if we talk about a covalent structure, you're also supposed to state characteristics of covalent compounds. So if it has a covalent structure, we expect you to talk about covalent bonds, you talk about the strength of those covalent bonds, and also you talk about how their melting and boiling points are going to be affected. In other words, you name a structure that is contained, and also you give features or characteristics of that structure. So looking at sodium chloride, it has an ionic structure. composed of sodium ions together with the chloride ions. You may ignore this for a moment. And then you see that ions are going to be together by strong electrostatic forces of attraction, simply because they are between oppositely charged ions. So this ionic bonding is what gives the sodium chloride its melting and its high melting and high boiling points. If you look at such an explanation, it's about presenting a structure and then you give characteristics of ionic compounds. So you say that it has an ionic structure containing ionic bonds which are formed or which are held together, in which ions are going to be held together by strong electrostatic forces of attraction, and they are going to have high melting and boiling point. You may also say that sodium chloride, due to the presence of electropositive and electronegative ions, is very polar, therefore it's soluble in polar solvents such as water. It's about how creative you are in terms of maximizing your marking points or your scores. Now proceeding to sugar, or what you can call glucose. This one has specifically a giant covalent structure because it's a covalent compound consisting of carbon, hydrogen, and oxygen atoms. So you have to talk about characteristics of covalent compounds. So covalent compounds, one, they are going to have covalent bonds, whereby, now we are going to look at this. But under covalent bonds are going to be formed simply by sharing electrons. For example, for us to form oxygen as a molecule, it has to share electrons with another oxygen atom. For it to form nitrogen as a molecule, it has to share electrons with another nitrogen atom. So these are what you call covalent bonds. And therefore, we told you that covalent bonds are going to be formed when electrons are being shared between two atoms of either the same element or different elements. So also sugar molecules are going to be neutral to form ions in solution because they do not form ions in solution. That's why they are neutral. They don't form either positive or electronegative ions. So and by that they do not conduct electricity. But like I said, if you look at the framing of all this answer or response, you realize that it's all characteristics of covalent compounds. What you have to do is to start by identifying the structure that particular compound has, then proceed it with the features or the characteristics that can be exhibited by that specific compound. So part C, let's look at why, or the reason why sodium chloride has a higher melting point than sugar. Now remember, we have already said that ionic compounds have stronger or have the highest melting and boiling points. And the reason for that is because of the electrostatic forces of attraction holding their bonds as compared to any other compound. So covalent bonds or compounds or covalent compounds have the weakest or have the lowest boiling point simply because for them they lack strong forces of attraction holding their atoms. So you're going to say that sodium chloride has a higher melting point than sugar simply because of the strong ionic bonds that are attributed by the fact of the strong electrostatic forces of attraction that exist between its ions. And these forces are very strong, and since they are very strong, they are going to require a large amount of energy to be broken down. And by that fact, it's going to lead to a very high melting point. If you're talking about boiling point, it's also going to consist of the same explanation, though instead of melting this time, it's going to be boiling. They mean the same things. So in contrast, sugar, we have analyzed that it's a covalent compound, so it's going to be joined by covalent bonds, and covalent bonds are the weakest bonds in chemistry or in chemical compounds. So you're going to say that sugar, being a covalent compound, is going to be held together by covalent bonds between the atoms with its molecules. So while these covalent bonds are strong with the molecules themselves, the forces between these individual sugar molecules are going to be very weaker as compared to the ionic bonds that are present in sodium chloride. And by that fact, this is going to take, if our two bonds are weaker, that means that less energy is going to be required to break them. And that's why, since sugar is a covalent compound with weak covalent bonds, it requires less amount of heat energy or less amount of energy to break the bonds holding its structure. this is going to result into a lower melting and boiling point. But since we only explain melting point, you simply indicate melting point. You don't indicate the boiling point. But like I've said, the explanation remains the same on both melting point together with boiling point. Now let's look at question 3. So question 3 is saying that in cold regions, calcium chloride is going to be used to melt ice on rods faster than sodium chloride. So task 1 is going to be requiring the explanation for the formation of 1 calcium chloride in terms of electron transfer. Then task 2 is going to require to explain how does the ionic structure of calcium chloride going to contribute to its effectiveness in terms of melting of ice faster than sodium chloride. And then part C, we are going to predict what is going to happen to the conductivity of an aqueous solution of calcium chloride when more water is going to be added. So let's look at the following responses according to that. So let's start with the formation of calcium chloride in terms of electron transfer. Now here you're simply describing formation of an ionic bond, and since we have already done this, let's just go this through the SC as quickly as possible. So you're simply gonna describe them just like the way we have described others. But if you look here, calcium is going to have 4s2. It's going to have 2 electrons on its outermost energy level. So for us to form a stable octet, we need to lose all these 2 electrons, but it's going to be donating them to a chlorine atom. Remember that a chlorine atom is having 7 electrons on its outermost energy level. So after getting 1 electron from calcium is going to be full. So the other electron of calcium is going to be placed onto another chlorine atom, and this is what you call the calcium chloride ionic bond formation. The calcium donates 2 electrons, but 1 electron goes to 1 chlorine atom and the other electron goes to another chlorine atom. So you're going to describe that by saying that calcium chloride, being an ionic compound, is going to be formed by electron transfer, whereby calcium with atomic number this, after stating the atomic number, you also state the electronic configuration. So it has 2 valence electrons in its outermost energy level. So to achieve an octet or a stable electronic configuration, it has to lose those 2 electrons. And when it loses 2 electrons, we form the calcium ion with a charge of +2. But like I said, calcium is going to lose two electrons. But the chlorine, each atom gains 1 electron. So that means that chlorine has to give 1 electron to 1 chlorine atom and the other electron to another chlorine atom. That's why in its compound, in the compound of calcium chloride, you are seeing that calcium is attached to chlorine atoms, simply because calcium donates its valence electrons to 2 chlorine atoms. So you're going to continue and say that chlorine on the other hand has atomic number of 17 with an electronic configuration of this. For the 3p subenergy level to gain stability, it has to gain an electron. So chlorine needs 1 electron to complete its outermost energy level to attain a stable octet. Now each chlorine atom is going to gain 1 electron, forming the chloride ion. So since 2 chloride ions are needed to balance the charge of the calcium ion, that means that calcium is going to donate to 2 chlorine atoms like I've elaborated here, forming the calcium chloride with this formula CaCl2. And make sure that the formulas are properly written. So in summary, calcium is going to lose 2 electrons to form the calcium ion and is going to donate them to 2 chlorine atoms, each chlorine atom gaining 1 electron, forming the ionic compound of calcium chloride. Now looking at part B, let's look at how the ionic structure of calcium chloride is going to contribute to its effectiveness in terms of melting ice faster than sodium chloride. Now we are going to look at this further in details as we proceed with our chemistry. But for now we are just going to look at the surface. So we're going to say that, but if you want to do more research, you look for a topic called colligative properties. But here we are just going to give a hint about it. So we're going to say that ionic structure of calcium chloride is going to play a significant role in its ability to melt ice faster as compared to sodium chloride. Now here, just a hint is that remember that we told you that these ionic compounds, they tend to dissociate. So if at all this compound dissociates calcium chloride, we form one calcium ion together with two chlorine atoms or two chloride ions. So the total ions that are formed by dissolution of calcium chloride, there are 3, because you have 2 chloride ions together with one calcium ion, which total up to 3 ions. But if sodium chloride dissociates in solution, we only get 2 ions. We get a sodium ion together with 1 chloride ions. So this one gives us a total of 2 ions. So the one that gives us a large total of ions in ice is going to make ice melt at a faster rate as compared to the one that is going to give us less ions in solution. So let's look at the elaborative explanation for that. So proceeding, let's look at the ionic dissociation. So when you look at calcium chloride, like I've just explained, it's going to dissolve in water, giving calcium ions and then 2 ions of chloride. So since it gives 3 ions, it's going to increase the number of ions that are going to be present in the solution as compared to sodium chloride. When sodium chloride dissociates, it's going to give the sodium 1 ion of sodium and 1 ion of chloride. So it's going to give 2 ions which are less than those given by calcium chloride. And with that, since more ions are present in the solution of calcium chloride, collisions with ice are going to be faster as compared to that in sodium chloride, and therefore calcium chloride is going to lead to a lower freezing point of water more effectively. I hope you have understood that. Now looking at the charge together with the ionic size, the higher the magnitude of the charge, the smaller the ionic radius. You need to know that. So if you look at both of the chlorides of the calcium and sodium, you'll see that calcium has a higher charge together with a smaller ionic radius as compared to sodium ion, which has a lower charge together with a larger ionic radius. So this in turn, the higher charge density of the calcium ion is going to lead to a stronger attraction between the water molecules, which further lowers the freezing point and cause ice to melt faster. So we're going to conclude and say that thus the ionic structure of calcium chloride, which produces more ions in solution and features a higher charge together with the smaller ionic radius, is going to contribute to its superior ability to melt ice faster than sodium chloride. Now let's look at the effect on the conductivity of the aqueous solutions of calcium chloride when more water is going to be added. So we are going to look at this also further in details under the topic of electrochemistry further ahead, but it's also important to give a hint on it from here. So when we look at that, when more water is being added to an aqueous solution of calcium chloride, the conductivity of the solution is going to decrease. And this is simply because conductivity in an ionic solution is going to be dependent on the concentration of ions. So when you add more water, now let's take it in this format. If at all you're having calcium chloride and calcium chloride is dissociated to give you calcium ions together with the chloride ions in solution, remember that electricity is going to depend on mobility of these ions. So for these ions to be freely mobile, there must be more water in this benzene as compared to the ions. So the more water or the more dilution you make, the higher the mobility of these conducting ions, and therefore the higher the conductivity. However, if you also put it in terms of per unit volume, remember that the higher, if at all water is present in diamonds, mobility is going to be very high because ions can freely move. But if at all you pick out one particular unit of that solution, mobility again is going to be very low per unit volume, but as a whole is going to be very high. So your explanation has to depend whether you are explaining in terms of per unit volume or you're explaining in terms of as a whole benzene. So here when you're explaining in terms of per unit volume, we are going to say that as we increase dilution, fewer ions are going to be present per unit volume. And if at all fewer ions are present per unit volume, that means that conductivity is going to become less. But if at all you're not explaining in terms of per unit volume, when you're explaining in terms of the whole basin or the whole trough, then conductivity will increase simply because ions are going to be freely moving in the solution. Like I said, we shall look at this later in details in the next coming topic and electrochemistry. So let's look at this. We are going to say that, however, after dilution, aqueous calcium chloride is going to remain conductive because it contains ions, which is the calcium and the chloride ions, which are proportional to the concentrations of ions in solution, and therefore more water is going to reduce the number of ions per unit volume and lowering electric conductivity, which is going to mean the same thing as this. But this on electric conductivity is going to lower per unit volume. When you get a trough like this and increase water molecules, the whole trough is going to have increased conductivity of electricity. But if at all you pick out a per unit volume, you pick out a square unit of that water molecule, which you call per unit volume, conductivity is going to be low simply because in that square unit you have picked out, we expect to have a very low number of conducting particles, which in turn reduces conductivity. So in this next series, you're going to be undergoing a discussion question. So you make sure that you take down this question and then you discuss it as a team with your class or with your colleagues or with your classmates. After doing that, you take it to your teacher for assessments to test your understanding. So you pause the video and then you take down the question. I'm going to be pausing after each and every 30 seconds. It's going to be a new slide. So the previous one was a discussion assessment. So this one is going to be the personal assessment. What have you understood and how are you going to apply the knowledge you have understood in answering daily life questions or scenarios or items that are going to be presented in your examinations. So you pause the video and then you take down the question. And so that was it for this video. Remember to like the video, share it to your classmates, and like the video. So see you in the next session, which is going to be either finalizing or continuing metallic compounds or metallic bond formation. We meet next session.